Welcome to Theme 3.2, where we will be discussing line integrals. So later you will learn about the line integrals, but before we go and jump into that, we can start off with some basics. So let's start with parameterization or parameterization. So parameterization is basically writing a function that is in terms of two variables in one. You can see it as adding direction to a curve with respect to time or another variable. So let's start with parameterizing some curves, which include a line, a circle, or a function. So let's start with a line. So what you need to parameterize a line is you need its initial position, and you need a vector of the line. So let's say you had a line that started at 1 and 2 and went to 2 and 4. And the direction, it goes from A to B. So note that there are some fundamentals that we apply as positive direction. So for a line segment and a function, it is positively oriented if it moves from the left to the right. And for a circle, it is positively oriented when it moves counterclockwise. But we'll learn more about that later. So the initial position is 1 and 2. To get a vector of a line, we just say the end point minus the beginning point times t. So this is your vector that you got here from saying the end minus the beginning. And this is your parameterized line segment. So now you have a vector that goes from this point to that point, and it starts at the initial position, and it goes along this line with this vector, which depends on t. So if t is a half, then your point will lie in the half of this line. If t is 1, it will lie here. So we say that t is an element of 0 to 1. This is always the case with line segments, that your t will be an element of 0 to 1 if it moves in the positive direction. So let's go to what it would look like in 3 dimensions. So in 3 dimensions, you will have an initial position of A0, B0, and C0. You will have this time, we can say time aspect, and then you will have your vector, which is end point minus beginning point. And then very, very, very important, it is very important to always remember what the boundaries of this variable time is. So for line segments, if it goes from left to right, it'll be t is an element of 0 to 1, because at time 0, it is at the initial position, and at time 1, it is at the end position. So another one is functions like y is equal to fx. You can also say y is equal to x squared or y is equal to square root x, but just generally a function where you have y and x, and x is in a certain domain on the function. So let's say you have y is equal to x cubed plus 2x. Then what you do is you say let x equal to t. So then you end up with y is equal to t cubed plus 2t. Usually you choose the easiest variable like x or y to equate to t, because let's say you equated y to t, then it would be very difficult for you to get x in terms of t, since you have an x cubed and a 2x. That's why we chose x to be equal to t, and this would give us y in terms of t. So now you have x in terms of t and you have y in terms of t, which will then give you this parameterized result. So this is your parameterized equation. So this is your x in terms of t, and this is your y in terms of t. And very important to remember is that t goes from a to b. Now, why it goes from a to b is because you let x equal to t. And x is going from a to b. So now t goes from a to b. And it would look something like this. Let's say this was your function. And x is in between a and b. So it goes from a to b. And also it goes from left to right, which is positive. The next one is a circle with your center CD and a radius of b. So for circles, we have an equation that we use to parameterize them. So AD or CD is where your middle point is. And then this part takes into account where the point is on the line of the circle. So let's look at the circle itself. So this is your midpoint, and then this is the point that we want to describe with one variable, which is t. So we use cos t and sin t because our convention is that x is equal to r cos t, and since r is b, because your radius is b, we just say b cos t. So it starts at c and d, and then you plus a length of b cos theta and b sin theta, and that's where you get your point. So I hope I'm making sense. So let's say this is your b. So b minus a, or c actually, but the center x value, which is normally 0, b minus c is b cos t. That's the difference in the x direction. And then c, let's say c is this point's y coordinate. C minus d is b sin t. So this just describes how far it moves from this point. And remember that circles are always positive when they are in the counterclockwise direction. So in a few moments, I will describe why I'm saying positive and negative. So sometimes you get curves that do not move in the positive direction, and you have to describe them even though they're not moving by convention. So let's say you had something like this, a circle that moves clockwise, or a segment that goes from B to A instead of A to B. What do I do? So first you can do is write it as if it was positive. So let's say it was positive, then you would have for the line segment, you would say it goes from A, which is your initial position, plus T times your directional vector. But noting that your directional vector is this coordinate minus this coordinate. So like we would usually have done it. And then very important, T is an element of 0 and 1. Well, 0 to 1. So if we want the curve as it is actually going, what we do is we reverse time, because it's not going in the same direction anymore. So we put a negative t here. But remember, you can't have the same initial position anymore because it's moving in the opposite direction now. So you just, for line segments, and mostly only line segments, you change the initial position, which will be at B. And then when you put a negative t in this place, now you will have a different directional vector. So it'll be A minus B. So these are just switched. And then, very important to remember, is that since you multiply t in here, you have to multiply t, negative t in here, which would give you, it goes from -1 to 0. So then if you want to change this to be in the direction that we have the curve, what you do is you have a negative t. So wherever there's a t, you take it and make it negative t. So here is our curve as it actually is. So we keep the same initial position because there's no t involved here. And then we multiply this by negative, but that changes the order inside of here. And very important to remember is that you also change this t to be -1 to 0. So you multiply what's inside here with -1, but you can't go from 0 to -1, so you have to say it goes from -1 to 0. So with the next curve, we have a 3/4 circle. So with circles, we have our normal equation that we use. It's the circle's midpoint plus your radius times cos t sine t, and then t is an element of the angle. So normally we would have the circle going in the direction of counterclockwise. So it would go from 0 to 3 pi over 2. But now we want to see what it actually looks like. So wherever t is, we have a negative t. So what happens is you put a negative t inside of the cos, but since it's cos negative t, the negative just falls away, and then this would turn to -3r sine t. But we also, very important, we have to remember to multiply this also by a negative. Since we can't go from 0 to -3 pi over 2, we go from -3 pi over 2 to 0. And that is just how you reverse your parameterization. We can't just work with the normal positive orientated curves, because when the direction is different, it might make a difference in an integral, for instance, or just the direction in general. So moving on to our first example, they're asking us to parameterize the curves C and give the negative C. So we have to take the curve that's been given to us and give them the opposite orientation of the curve. So our first curve that we've been given is a half circle, and it is counterclockwise, so that is our normal positive orientated curve. So our radius we can see is 2, and our midpoint is at the origin 0, 0. So our C, which is our positive orientation, would just be 2 cos t, 2 sine t. But if you are used to the normal way that we write it, it would just be 0, 0 plus 2 cos t sine t. And t is an element of 0 and pi, because it goes from 0 to pi. So just remember this part, it's very important, and I will keep reminding you of that. So if we want the curve going in the opposite direction, then we just take t and make it negative t. So then we will have 2 cos t and minus 2 sine t, and t will go from negative pi to 0. Now for the next one, we have a curve which is a function, y is equal to x squared, which goes from right side to the left side. So note that this is actually the negative direction, but we can work with that. So let's start with what it would have been if it was in the positive direction. So let x is equal to t, and then y is equal to t squared. That's just what we normally do with functions. So then your negative c, so if it was in the opposite direction, would be rt, which is t and t squared, and t would have gone from 1 to 2, because x goes from 1 to 2. Now, if we want the curve that we actually have, which is in the negative direction, we just have a negative t in front, which would give us negative t and t squared, and t would have been an element of -2 to -1. So that is just some examples of parameterization. The next one, we have kind of ellipse. So with an ellipse, it doesn't work quite like a circle. It works more like a function. But you can work it as a circle as well, but you'll have to manipulate some things. So the equation for this ellipse is x squared over 16 plus y squared is equal to 1. So let's write this in a kind of x squared plus y squared type of scenario, which would look like this. So we have this plus this is 1. Now, doesn't this look a bit similar to sine squared theta plus cos squared theta is equal to 1? Yes, it does. So what we do is we say x over 4 is equal to cos t and y is equal to sine t. So now we can get x and y in terms of t. So when we do that, remembering that it's going in the clockwise direction and it's negative, so our positive orientation would have been 4 cos t sine t, with t going from 0 to 3 pi over 2. But since we don't have that curve and we want the curve that goes clockwise, we just put a negative t, and that gives us 4 cos t minus sine t, and t that goes from -3 pi over 2 to 0. So that is how you reverse parameterizations.